Welcome back to Codex. Our speaker today is Joe Kileel from UT Austin. Professor Kileel is an expert in the mathematics of data science. Today he'll tell us about covering numbers of real algebraic varieties. Take it away, Joe.
Thank you. Thanks to the organizers for the invitation. Happy to be a part of this really nice seminar. Okay. So this is joint work with a really talented PhD student at UT Austin, uh, who I'm advising, Yifan Zhang. And just keep an eye on him. He has a lot of ideas and energy. So this is all joint with him. So the talk is about covering numbers of algebraically defined sets. So let me first recall what covering numbers are. So if you have some subset V, in general, just in a metric space, then for any positive epsilon, the epsilon covering number of V, denoted by NV epsilon, is the smallest number of balls of radius epsilon centered in V needed to cover V. Okay, so this picture here is indicating a covering of the interior of this black curve in the plane, and we're covering it by epsilon balls here. Okay, and just for simplicity here, we are going to require the centers to be in the set V. Slightly changes the covering number otherwise. Okay, so this is the basic definition. And why are covering numbers important? Well, clearly they give some notion of the size of a set. So they can be used trivially to bound the volume of a set, right? The covering number times the volume of an radius epsilon ball is an upper bound on the volume of V. And actually, you can also bound the volume of tubular neighborhoods of V. So if a set of centers gives an epsilon covering of V, then if you increase the radius to 2 epsilon and keep the centers, then you obtain a covering of the epsilon tubular neighborhood of V, where you fatten the set V at every point by epsilon. So just by doubling the radius, you cover tubular neighborhoods of V. And these are of interest, volumes of tubular neighborhoods are of interest, for example, when the set V has an interpretation as the failure set of some algorithm. So for example, where could represent the set of inputs to a computational problem where the condition number is infinite. And then the tubular volume represents inputs where the condition number is very large. You might like to know sort of what's the volume of such bad inputs. Okay, and that this has indeed been one way covering numbers have been applied. Another application of covering numbers is coming actually from dimension reduction. And so when we try to project, if V, say, is in some high dimensional Euclidean space, and we'd like to project V to a much smaller dimensional space while preserving pairwise distances approximately, as in, say, the Johnson-Lindenstrauss lemma, then you can obtain bounds on the required the dimension down to which you can reduce in terms of the covering number. So this naturally arises in dimension reduction as well, covering numbers. It also has applications in topological data analysis. So if one is trying to estimate homology of some space, topological space from random noisy samples, then the covering number of the space roughly tells you sort of how densely you need the samples to be to capture the correct homology. So that's also an application of covering numbers. Okay, so the setting is really in general, but we're going to focus in not just on a subset of a metric space, but actually a pretty nice subset, one defined by polynomials. So we're interested in sets V that are defined by polynomial equations. So V is in some R to the capital N, and it's defined by polynomial equations in capital N variables and potentially polynomial inequalities as well. So we focus here on real varieties, by which we mean zero sets of systems of polynomial equations, and also images of polynomial maps. So the set V may be parameterized by a polynomial map P. And we mean here the exact image before taking closure. Okay. So one application I'll come to later in the talk is actually low-rank tensors. So tensors and tensor networks with low-rank decompositions naturally, the set of them naturally is the image of a polynomial map. The tensor decomposition itself gives a polynomial parameterization of the set. And so we're going to be able to actually bound the covering number of low-rank tensors and get some interesting, some amusing conclusions from that. Yeah, the first bullet is indicating that in algorithms where sort of the operations are just basic arithmetic, often the set of ill-posed inputs are actually described by polynomials. So we're not losing too much even for the ill-posed input applications. Okay, we're also actually going to be able to use the real algebraic varieties to say things about neural networks. So this why neural networks can be captured by polynomials, this is less obvious. So firstly, if you take the activation functions in the neural network to be polynomial or rational functions, that is the ratio of two polynomials, then you're in the framework that I'm going to be presenting today. But actually, we will also be able to make statements for ReLU neural networks, where there's just piecewise linearity. And there will, the idea is that we're going to approximate ReLU by rational functions. So even sort of non-polynomial sets, if you can say how you approximate them by polynomial, you can get conclusions about them, and we'll see that for ReLU networks. Okay, so in these problems, what you want is a good upper bound on the covering number of underlying varieties or polynomial images. Okay, any questions about the motivation? Thanks. Okay, let me just jump to the technical contribution here. So U here is a set in f to the n, where f is either the real numbers or the complex numbers. And U could be semi-algebraic, meaning that it's defined by polynomial equations and inequalities, or it could be an algebraic variety, here meaning that it's defined just as by the vanishing of polynomial equations, or it could be the image of a polynomial map, any three of these. And let's say the relevant polynomials in the description of U are Fi, and we'll assume that there's a universal, that there's an up bound on the degree of all the FIs, which is little d. And we're going to be focused primarily on the setting where the set U has big codimension. So the dimension of U is at most little n, and that's much, much less than the ambient dimension capital N. Okay. So then there are some prior results on covering numbers for algebraic sets. And here's a table. So Yomden and Comte gave results for general semialgebraic sets with in Rn with m constraints, and you intersect. I mean, when we talk about covering numbers, we need bounded sets. So we're going to intersect the set U with the unit ball. This Bn is the unit ball. Okay, so I'll report bounds on the so-called metric entropy, which is the logarithm of the covering number. Okay, so Yomden had this upper bound, little n, that's dimension times 1 over epsilon. Okay, this here is what you would get if your space were just a linear space. If you were just a linear space of dimension little n, you would just obtain n times log 1 over epsilon. But then there are additional terms accounting for the nonlinearity of U. Okay, and so you see this and sort of this the ambient dimension, the degree of the polynomials, the number of constraints, they're all appearing in these additional terms. And these additional terms are not negligible. And in fact, they can look a little scary here because you see like a super linear dependence on the ambient dimension, capital N here. Okay, this is a big term. Here are other result settings. So here we have a variety, so no inequalities, just equations. We intersect again with the ball. There's a result also when the base field is the complex numbers and you have a projective variety. There's a result of lots where one has a smooth complete intersection. So this is a variety defined just by equations, but there's some conditions, some geometric conditions on the equations here that they're sort of algebraically independent. This was one setting. And finally, Basu and Liario result for general real algebraic varieties. Okay, and these are the various results. Okay, so you're always seeing intrinsic real dimension times log 1 over epsilon with correction terms. Okay, and there's here you'll see one sees sort of better. I mean, it's little n is much less than capital N, so these were significant improvements over the 2004 results. Okay. So here's what we're contributing to this picture. Firstly, for semi-algebraic sets with little m inequality constraints. So just inequalities. There's capital M here also for Yomden also included equalities. We get this. So this here is an improvement on what you're seeing with Yomden. In particular, there's a little n times log capital N. So there's there's an improvement there. For the variety case, we match Basu Lorario's result in order, but by a completely different argument, and an arguably much simpler argument. And really where we get the best applications is for sets with polynomial parameterizations. So when V is the image of a polynomial map from R little n to R capital N, and the degree of the coordinate functions of P are at most D, then this is the upper bound on the metric entropy we obtain, and there's notably only a log dependence on the ambient dimension here, capital N. So the setting of polynomially parameterized sets, that, as far as we can tell, it wasn't in these prior works, and in our theory, there's a big difference. Okay. So that's a lot to take in this table, but let's press on. So I want to give an idea for the proof, and it's actually a very intuitive approach. What we have a roughly a induction argument on the intrinsic dimension through a slicing argument. So we're going to intersect our set V with a bunch of linear subspaces, and in the intersection, the intrinsic dimension will be one less, and then we'll slice again, and so on. Okay, so in fact, this argument leads to a upper bound on covering numbers for a larger set, a class of sets, than just the algebraically defined ones. So we can actually, just by virtue of the proof, where we're slicing with linear subspaces, can actually get covering number bounds for what we call so-called regular sets. So this is not a standard term here. Okay, so a set V in Rn is going to be Kn regular if so for almost all affine planes L of codimension n strictly more than n, little n, V intersected with L is empty. Okay, so this is the first condition for being regular, and this basically is saying that n is like little n is the intrinsic dimension of V. So if I try to intersect V with a linear space of two low dimension, then it's actually going to miss V almost always. This almost all is with respect to an invariant measure on affine planes. So there's a natural measure here on affine planes. Invariant with respect to rigid body transformations of the planes. And the other condition involving capital K is that for almost all affine planes that should be meeting V, so that is their codimension is less than or equal to little n, the intersection V intersect L has at most K connected components. Okay, yeah.
So this regular, the second condition is sort of using a way to make a sort of notion of degree. Is that what I should think of K then, as some sort of
Yes, you
degree,
should
analog of degree?
indeed, yeah, you should think of it as like an analog of degree for capital V.
Okay.
Yeah. And yeah, so these two parameters, one is like an analog of degree for an algebraic variety, and one is it's like the dimension. Okay, and so I mean this doesn't algebraic varieties are included in they are regular, where little n is the dimension of the algebraic variety, and capital K can be bounded in terms of the degree. So by the Milnor-Thom theorem from real algebraic geometry. But actually other sets also are regular. So for example, something that's trivially regular is any convex subset of a linear subspace in Rn. Like with a transcendental boundary or whatever is regular. Okay, so yeah, many sets of interest are indeed regular. So all the sets I mentioned, so polynomial images of polynomial maps, zero sets of polynomial equations, and also you can add in polynomial inequalities as well. Okay, so here's a lemma. So this is a big family of regular sets. And here I'm giving you explicitly what the k and n parameters are, which we'll need. So suppose P is a polynomial map, and the coordinate functions are bounded by degree D. Then the image of P is regular with these parameters. So the intrinsic dimension should be the dimension of the domain of the parameterization, and then the K here turns out to be 2 times the degree to the power of n. Okay, if you have a zero set of equations of degree at most D, then that's regular, but the K now can be quite a bit bigger. It's 2D to the power of capital N. And you can do operations like taking a regular set and scaling it to the sphere, to the unit sphere in our capital N. That preserves regularity, and we can say what it does to the parameters. And you can also, if you intersect a regular set with a ball, that also preserves regularity, but you have to tweak the K parameter. We can tell you how to do that as well. Okay, so yeah, underlying what tells you that the algebraically defined sets are Kn regular is this so-called Milnor-Thom theorem, which is bounding the number of connected components of a zero set of real polynomials. So this is the hammer that we use. Okay, here's our main result. So you saw it in the table, but now I'll be more precise. So let V be in R to the capital N, and it's inside a box from minus a box minus t to the power of n. Then for any epsilon, any radius epsilon less than the diameter of V, we have this bound for the log covering epsilon covering number. It's at most intrinsic dimension times this log here plus log 2k. And so you can rearrange it to have it in the form that corresponding to the table. Rearrange it with big O notation. So this here, yeah, this is a general result for any Kn regular set. And then to get the results in the table I showed before, you plug in the correct values of K and N for the different cases, a variety, polynomial image, semi-algebraic set, using this lemma, telling you what K and N are. Okay, so here's our this is the master theorem for any Kn regular set. Okay, let's give some comments on the proof. So there's an induction by slicing. That's the main proof idea. So suppose we started with this V in R3. It's this blue surface. What we will do is create a grid of 2 planes in R3 in the 3 different directions and slice up our blue surface. Okay, and then so parts of the blue surface will be in the interior of cubes in this grid, and then other parts will be on the boundary of some cube. So on the boundary of the cube, you'll see curves, like on the left. And we can also have a grid of now lines in the plane. So this picture on the left is like on one face of the cube. We can have a grid of lines cutting this curve up as well. And so some parts of the curve are intersect some of these lines, and other parts are in the interior. Okay, so having done this, so created these grids, we can then construct a covering of our set. So if we look first on this boundary curve, what I want to do is I'm going to place a ball centered at each one of these red intersection points, big enough that it contains all of the cells adjacent to this red intersection point. So it should contain this cell and this cell below. And then that'll take care of that'll take care of this segment of the blue curve here. And we likewise do that at all these red intersection points, and then also intersection points for the lines in the other direction, for the other lines. So so you get control in this way on the size of the balls that you're using, because it's just a size needed to cover adjacent cells. And then you also get control on the number of balls, because that's the number of intersection points with grid lines. That will result in covering this entire boundary curve. Okay, and then there's some sort of induction that enables one to go 1 dimension higher. So and it leads to this recursion. Yeah, so okay, so this picture is the rough idea. Okay, there's a question in the chat, maybe. Okay, no, there's not. Okay, let's go forward. Okay, oh yes, one important thing before proceeding. Another possibility is that there are some connected components of this intersection that are completely contained inside one cell, right? Such as this green circle. And we also need to cover those. And they may be missed by in this case, they will be missed by the process I just described of putting balls at the red intersection points. So for this, we have to also control the number of connected components of this intersection. That will be an upper bound on the number of such guys. And then for them, we just place a ball at the center of their cell and cover. So yeah, that's the other piece. Okay. How good is the bound? So the dependence on the box size is optimal. That's this dependence on T. The dependence on K is also optimal. You can see this by taking V to be a set of discrete points. You would need to, if you have well-separated discrete points, you'll need at least K balls. So so the metric entropy needs a log K. The dependence on epsilon is optimal at least as epsilon gets small. And this is because this metric entropy divided by log 1 over epsilon in the limit is an upper bound on the Hausdorff dimension of a set. Okay, and then that equals n. So back in this result, in our main result, we had a capital N to the 3 over 2. So that's this constant in front of log n. This 3 over 2 may be optimal. We have a heuristic argument for why a 3 over 2 here seems needed. But that may be one place for improvement, okay, in the constant in front of log n here. Okay, but generally this is a tight bound, at least for regular sets. Okay. Let's proceed to say some things about tubular volumes now. So as I mentioned, if xi are centers of an epsilon covering of V, then the union of the balls at xi of radius 2 epsilon covers the epsilon thickening of V. So bounds you get a bound on the tubular volume as the covering number times the volume of a radius 2 epsilon ball. Okay, so this is a corollary. And here we look at, sorry, this should be a subset, an image of a polynomial map whose coordinate functions have degree at most d. So for polynomially parameterized sets, this is when our theory is most powerful. Then the dimension of the yeah. So okay. Suppose P is a point in R to the n and sigma is positive. We're going to let X be a random point in the ball centered at P of radius sigma, and look at the probability that X is within distance epsilon to V. This is one way of capturing the tubular volume. Okay, I mean, it also, yeah. So and this is the bound that one obtains. So so X again is drawn uniformly from just some ball in Rn, which centered at P radius sigma. And the probability that that point is within epsilon of V, log of that probability is at most this. So okay, this. Yeah, well, we can get this. So yeah, let's see what we can. So we will apply this here now to a particular set V that has been of interest, and see what probabilities we actually get. Okay, so our set V will be low-rank tensors, consist of low-rank tensors. So for people who don't know, a tensor is, we'll think of as just an array of numbers, a dth order array, and n1 by n2 up to nd. It's like a higher order matrix. They arise, in a host of situations, data might naturally be organized in an array if there are sort of more than two attributes defining each data point. You can naturally put like a 3D image then as a third order array where each direction is corresponding to a spatial direction, or actually moments of multivariate distributions are tensors, and also derivatives of multivariate functions evaluated at some point are tensors. These are like higher order versions of covariance matrices and Hessian matrices, respectively. And so these are fairly ubiquitous. And a salient thing about them is that they're very big. So, you have n1 times n2 up to nd numbers here, describing one tensor. So there's lots of different compressions of tensors people work on. Maybe one of the most standard and useful is the canonical polyadic or CP decomposition. And this is a generalization of low-rank matrix decomposition. So this should be an approximate here. But we try to approximate X as the sum of outer products of vectors here. So this picture is just visualizing an outer product, but some operation that accepts three vectors and returns a third order tensor whose entries are the triple-wise products of entries of the three vectors. Okay. So you try to symbolically or try to have this equation. And on the left, there are n cubed entries in X, but on the right, there are only 3 capital R times n parameters describing the decomposition factors, the CP factors. Okay, so the CP rank is the minimum number of rank 1 tensors needed to exactly get T. This is the exact CP rank. Okay, so question I want to ask is, how close is a random tensor to its best low rank approximation? So this is a subtle question because best low rank, the infimum here may not be attained actually. So low rank tensors do not form a closed set. But just sort of disregarding that subtlety, I mean, the question here makes good sense, even though the infimum may not be attained. I want to know what the how close a random tensor is to being low rank. And this question can be interpreted, can be approached through volumes of tubular neighborhoods of low rank tensors, and low rank tensors are a polynomially parameterized set. So we can apply our theory to give a cover number bound on the CP tensors and then a tubular volume bound on CP tensors. So here's what you get. So V here is the set of n1 up to nd tensors whose CP rank is at most R. N bar will be the average dimension here. Okay. And we'll take any epsilon between 0 and 2t. So we're going to intersect low rank tensors with the ball of radius t here. And this is the bound on the metric entropy one obtains. Okay, so it's just some formula. We'll interpret. We'll plug in numbers in a moment. Okay, if in fact the rank is really small, so the rank R in the number of rank 1 terms in the CP decomposition is less than the minimum dimension here. So this is the so-called undercomplete case in tensor decomposition. Then you get an improvement in this covering number. So you get to subtract off this extra term here. In the low rank case, so that the covering number drops further. Okay. Yeah, so let T here be a random tensor with IID Gaussian entry, so standard Gaussian entries. Suppose we our tensor is sort of not super small, so it's at least 2 by 2 by 2. And let's let A here be the event that there exists a tensor T prime of rank at most R, that is, whose angle is at most epsilon from our random guy T. So, so I want to know the probability that my random Gaussian tensor is within an angle of epsilon to a low rank tensor. And we speak here about angles because CP rank is preserved under scaling. So angle is the natural distance here. This is a result. So I'm reporting this result in the undercomplete case. Then for any angle less than 30 degrees, the probability is upper bounded by this expression here. Okay. What are these when we put in numbers? So let's take third order tensors, 100 by 100 by 100, rank 30. It's undercomplete. All these constants here, they're at most 3. You can check the details of the proof, so we can set them to be 3 to get an explicit bound. And the probability of our random 100 by 100 by 100 Gaussian tensor being within 30 degrees of rank 30 is at most this exponential e to the minus 40,000. You want to be within pi over 7 radians, that's even smaller. Probability of at most e to the 140,000 here. So interesting that you actually get sort of astronomically small probabilities here. And that's just telling that there's really content in this bound. Okay. And as someone who likes tensors and low rank tensors, what does it mean that a random tensor it's extremely unlikely for a random tensor to be low rank? The way I interpret this is that the tensor has to have some sort of underlying structure for a low rank approximation to be reasonable. So if you really have no model or structure behind the tensor, then it's just not reasonable for it to have a good low rank approximation. It's exceedingly unlikely. So there's some reason why. And fortunately, in practice, there is structure behind tensors that enable low rank approximations to be useful. Okay, so how much time do I have?
Oh, at least 6 minutes, lower bound of 6 minutes. But then there's questions after. So, I mean, really,
yeah,
13 minutes.
Yeah. Okay, sure. So let me quickly go over the application to neural networks. So I'm going to start with this is a refresher on statistical learning here. So data sampled from a distribution D, labeled data. We'll fix for a hypothesis class and some samples, training samples. The goal here is to minimize the empirical risk. So it's minimizing over the hypothesis class, sum of losses over the training data. So F is the variable here. Okay, so this is the empirical risk. The population risk, that's when we take an expectation over the distribution. And the generalization error is like this worst case gap between the empirical risk just based on the random data I got and the population risk. Okay, so one likes the generalization error to be small because then it means that uniformly over the hypothesis class, the empirical risk is like a good proxy for the population risk, which is what one probably really wants to minimize. Okay, so yeah, we'll look at a setting where the hypotheses take values between 0 and 1, and the loss function is Lipschitz. And this is a somewhat standard setting for classification. We can actually get results here for two different hypothesis spaces, networks, neural networks with rational activation functions, where the numerator, where the degree of the numerator, where the numerator and polynomial and the activation functions are both polynomial, and their degree is at most s, and possibly these rational activations could be trainable. So their coefficients, one may be training over their coefficients as well. Okay, and then this rational neural networks were introduced by or were studied by some numerical analysts sort of recently, and they actually can be quite performant. Also, we'll look at ReLU networks where the weight matrices are uniformly bounded. Okay, how do we tackle generalization error? Well, the Rademacher complexity is a standard tool. So the Rademacher complexity of the hypothesis class and loss on some on the training data is defined as follows. Okay, it's the expectation over a Rademacher random vector here, sigma. So these are random signs, plus or minus 1. And then we're looking at the largest that this takes. Right, so the expected maximum of Rademacher's twisted sum of losses. Okay, so the point is that this Rademacher complexity gives an upper bound on the generalization error. So this is a standard result. Everything on these last few slides is standard and known. Okay, so our goal is really to control this Rademacher complexity. And there's a tool for that called the Dudley's integral. So the Rademacher complexity in turn can be upper bounded by this integral of the square root of the metric entropy. We're integrating here over epsilon, the radius and the covering number. Okay, so this now gives us our connection with covering numbers. So what is our set? What is our set V? So for us, it's this. So we fix training data, x1 through xn, and then we apply to it all possible hypotheses in our class, so all possible neural networks with a specified architecture. This gives us some subset of Euclidean space, and that's our set V. That is arising in Dudley's integral here. For rational networks, so where the activation functions are rational, it's actually a regular set. I mean, everything is polynomially described, so this is a regular set. For ReLU networks, what we do is we approximate the ReLU activation with rational functions at the different layers with different accuracies, and we end up approximating this by a regular set. Okay, and this here we've taken out the loss function. You put the loss function in at the end by just using Lipschitzness of the loss. So this lets us just directly work with this set here. even though Dudley's integral has losses. Okay, so these, just real quickly, this is what we get. So for rational networks, we have an depth L with D, fully connected rational network, possibly trainable activations, numerator denominator degrees are at most S. The loss function is 1 Lipschitz. Then this is the bound. This is the bound one obtains for Rademacher complexity. And it's sort of comparable. So I mean, it's actually, we don't find results directly in this setting in the literature because rational neural networks are not as studied. But in the most analogous case we could find, this is actually improving. This is an improvement by a factor of D. Okay, for ReLU neural networks, again, fully connected depth L with D. All the weights we assume are bounded by W, by universally, Lipschitz loss. We obtain a bound on the Rademacher complexity, and basically this is matching state-of-the-art bounds, as far as we can tell, for generalization error of ReLU networks. But by a completely different approach that replaces the neural network by an algebraic variety and applies a covering number to that. Okay, so that was it. So here I talked about covering number of algebraically defined sets. There was a slicing argument. We applied this to CP tensors, and we're also to neural networks. And as I just mentioned, we're able to recover generalization error bounds for ReLU networks. There's one more application in our paper, and that's to polynomial optimization. But I'll refer you to the paper for that. Okay, thank you.